Hi, everyone. Welcome to Ray's Defense. My name is Sophia Merrifield, and I am Ray's advisor, and I will serve as the chair of the committee for today. I just want to give a few procedural comments. So first, Ray will give a public seminar of about 45 minutes, followed by time for audience questions. After this public question and answer, we'll ask everyone to leave this room, and we'll just meet with the committee to do an internal session. And we will ask that during that time that you go to Surfside, and pending positive or negative outcome, we will be there to celebrate or commiserate with Ray. I want to make a few acknowledgements before I hand it off to Ray. The first is to thank the committee for their time and guidance. That would be from Mechanical and Aerospace Engineering, Mark Anderson and Sonia Martinez, and from SIO, Dan Rudnick, Bruce Cornell, and Eric Terrell. I want to acknowledge a few scientific collaborators that have had an impact on Ray through his time here. The first is Hunter Akins, who is an AOS student in underwater acoustics. I think is now a project scientist here. The second is Matt Masloff, who provided some important model output for one of Ray's published papers. The third is Seth McCammon from Hui, who also provided some important model output and scientific collaboration. And the fourth person is Luke Rainville, who is the chief scientist on a 35-day cruise in Iceland that Ray was sent on by himself with our other student, Ali Ho. I also want to thank Ray's family for their support, to his dad, Wes, his mom, Margie, his brother, Bobby, and to his new wife, Allie. Thank you for your support, Ray, through this chapter of his life. You will find some fun fieldwork photos of Ray as I go through this quick introduction. I want to just give a little bit of background on his time. So Ray comes to us as a 2016 graduate from Davis Senior High School. He started in Cord C, which is our lab here at Scripps, in 2018 as an undergraduate engineering aide, almost exactly 8 years ago. I looked it up. In 2020, he got his bachelor's degree in mechanical engineering, graduating cum laude, and then he transitioned into the AOS program here at Scripps, and he was awarded a prestigious NDSEG National Defense Science and Engineering Graduate Fellowship in 2022, which funded his research. And he's been extremely productive during his time here. He's been a first or co-author on 7 conference papers, and a third and 3, almost 4 first and co-authored journal publications. So very productive and a really solid body of work. He's also been very committed to education. So here are some photos of him giving kind of conventional and unconventional lectures. So you'll see him giving a lecture on the EV Nautilus, which is a ship we were on. You'll see him giving a lecture at Cosmos, which is a summer program here at Scripps. And then finally, you'll see him actually teaching as an instructor of record, MAE 142 in the summer. And I will invite you to ask him why there is a video of a chicken in the background of his lecture at the after party. Ray did spent a lot of time in the field over his 8 years at Cord C. He has been on 6 cruises and a total of over 3 months at sea. And he had the opportunity to sail off of Iceland, Palau, Saipantinian, and Rhoda. And here's some images of that. And I think what's really important is that he got an appreciation for a lot of the robotic vehicles that we work with. So you'll see wave gliders and different buoyancy gliders in the pictures here. And he really had kind of a practical education in the challenges of running these systems at sea. And so then you might wonder, wow, this guy's done so much time at sea. We're going to hear all about this data he's collected in his thesis. And it turns out you will not. And I will take some credit for that by putting it in some unsavory situations at sea. So here's Ray seasick on a small boat where he's the only one sitting in front with a sad face as he almost pukes. Here's Ray preparing to go on a small fishing boat into a very crappy sea state. And then lastly, here's Ray in his Fallies in hailing rain, starting a 4-hour deck shift. And I think that might have caused him to be more interested in simulations. So it's been such a pleasure to work with you. I'm so proud of the body of work that you've put together. I'm so excited for you to present it today. And it's really my pleasure to introduce Ray and to pass the baton to him.
Is that looking good on Zoom? Okay. Yeah, thank you so much, Sophia, for the introduction, and thank you to all my committee for being here in person and online. And today I'm going to get to present to you my thesis on energy optimal path planning in ocean currents. And so if you're not familiar with path planning in the ocean, you might actually be very familiar with it in your day-to-day life. So every day when I wake up, right over in grad housing, I want to get here to Scripps in the fastest way possible, or usually in the fastest way possible, but I can't necessarily go in a straight line. So maybe I'll ask Google Maps how to get there, right? And this is the way I usually take. It's the most direct and it's the quickest, but I could also think about optimizing for something else. So maybe I want to avoid the most sort of congested parts of campus, or maybe I want to take some side roads to avoid traffic. But either way, I have different options to get from point A to point B. So in the ocean, we have the same problem, but instead of sort of dodging cars or switching streets, you have to deal with moving through a fluid that is in itself moving. So this is a problem we've been thinking about for hundreds of years, and this is actually a chart from Ben Franklin back in the 1700s, where he was corresponding with local ship captains, talking about how they could use the Gulf Stream to more efficiently navigate between the US and back to England. Right, so on the way there, you might want to ride through this current, and on the way back, most importantly, you want to avoid it so that you can make way and be efficient. But we're still thinking about this today, especially in the context of knowing so much more about the ocean through more complicated ocean models. So here is a picture of the Gulf Stream from a more recent model output from NASA, where you can see not just this sort of solid strip of currents, but you see so much dynamic ocean eddies and fronts moving around that we might be able to take advantage of to improve planning. And so when we think about planning, we also want to think about which vehicle we're thinking about the problem for. So we can classify vehicles by their speed on the x-axis and duration on the y-axis. And planning for something like a container ship that's going very fast and might be out for about a month is going to be very different than piloting an environmentally propelled system like a wave glider or slocum glider, which you can see on the top left, where they're going less than a meter per second, but can be deployed for over a month and up to over a year. But what we're going to focus on for most of the talk today is a propeller-driven AV. So these are vehicles that are a little bit more agile than environmentally propelled systems, going sort of nominally about a meter per second. And they can be deployed for around anywhere from a few hours up to 2 days. And this is because we need to think about how fast they're going with respect to the ocean currents and how we might need more information given these slower vehicles, right? So for a container ship or back in the day where a vehicle is going much faster than the current speed, planning is maybe not as hard or not as interesting. But here, where the vehicle speed is sort of on the same order of magnitude as the currents, we can really start to care about all this small scale dynamics in the ocean. And so just as we've been thinking about it for hundreds of years, we've been studying it more formally for about the last 100 years. And so a German mathematician, Ernest Zermelo, formulated this problem in the 1930s. And this is a translation from the original paper, which has now become a very canonical optimal control problem. So we're talking about planning through a vector field, so either wind or ocean currents that are given by, so they represent a flow that changes over space and time. He talked about a ship that moves with constant velocity relative to the surrounding air mass. So our vehicle or ship on the bottom, its velocity is going to be the sum of wherever it points, and then the ocean currents at that position. And then the goal is how must the ship be steered in order to come from a starting point to a given goal in the shortest amount of time. And we're still using this almost exact problem formulation with two sort of material changes. So A, we're going to be considering vehicles that have control over their velocity, so it can choose both its direction and speed through water. And this naturally leads us to talking about paths that minimize energy. So if you want to get somewhere in the shortest amount of time, you'll drive the vehicle as fast as it can go. But if we want to minimize energy, we might speed up or slow down depending on what the ocean currents are doing around you. And so if we state this a little bit more precisely, we're going to say that the vehicle's state or position x, and therefore its velocity, is the sum of v, the control, with the ocean currents. That might be a function of time, as well as the position that the vehicle is at. We're going to consider an energy consumption model that has two terms. The first term is going to be dynamic energy consumption, so it's going to change as a function of time based on what you're controlling. And that's going to be the magnitude of v to the power of 3, and then scaled by alpha, which we'll call the dynamic power coefficient. And this is a function of vehicle geometry, so hole size, drag coefficients, things that can be calibrated to a specific vehicle. Beta is going to be a term that's constant in time, representing the hotel load. So all of the power that you need to keep a system up and running, be that command and control, onboard computing, or other sensors. And the problem that we're solving is going to be to find V star, which is the optimal control as a continuous function of time, which minimizes total energy consumption. So we're integrating from the given start point to an unknown endpoint, but we specify where the vehicle starts and ends. And so this is a very well-studied problem. And in the last 10 years or so, there's been a lot of development using finding solutions to these problems using complicated partial differential equations that govern the evolution of what we call a level set. So in the figure on the right, if you can see, we're starting in the center here. The goal is to get to this star in the top right, and there's a simple jet of currents going from left to right across the screen. Each of these contours in black or green represent all of the states that a vehicle can reach in a given amount of time. So you can see on the bottom of the screen where there's no currents, these level sets just propagate out sort of uniformly or concentric circles, but they're going to be distorted by the currents along the way until they reach the endpoint, at which point you can find the optimal path. So these have been, like I said, developed a lot over the past 10 years, starting by Lola et al. In 2012, and they've been extended to three-dimensional currents, uncertain currents in 2D, and then more recently dealing with energy optimal solutions, both in 2D and for a Pareto optimal solution, trading off between time and energy. So why they've been so successful or why they've been so widely adopted is because they are sort of very rigorous. So they're provably optimal and complete, meaning that if you can find a solution, or if a solution exists, the algorithm will find the solution, and it is guaranteed to be globally optimal. So it'll give you back the path that is much better than anything else. However, you are solving a very non-trivial PDE, and to do that on a computer, you need to discretize the environment and solve over some sort of mesh, which gets very complicated, requiring much finer discretization, especially in sort of complex ocean currents that might vary in 3D in time and have complex bathymetry, such as this example on the right. So another way to approach this problem is by formulating our solution in the form of ordinary differential equations, or ODEs. And this is the technique that we're going to be talking about a lot in Chapter 1. And the major pro is that they're much more computationally straightforward. So on the figure on the right, before, if we see the level set in the background, instead of advancing an equation that exists over the entire domain, we can specify ordinary differential equations that might correspond to individual ones of these green trajectories or rays. We can shoot all of these out in parallel in a much more straightforward fashion, and we can find an optimal trajectory like this red option that starts starts from the starting point and then reaches our desired goal point. However, they have a much weaker sense of optimality. So they have what we call a necessary but not sufficient condition for optimality, meaning that there's some sort of ambiguity. So if we change our goal point to this star on the bottom right, we might have two locally optimal trajectories that both cross the same point. Right? And so our algorithm or our method isn't going to necessarily tell us which of those is correct, but it allows us to now pick from a finite subset of paths. And so this is equivalent to maybe a schematic you've seen before, where you're looking for the global optimum of some one-dimensional function. Viewing the entire function is similar to being able to propagate level sets, whereas just checking the local derivative, setting it equal to 0, is sort of looking at our extremal trajectories. And so these have been studied in the ocean, but in a much sort of more limited sense with respect to the level sets. So this is a very nice figure from a nice paper of Russ Davis here at Scripps a while ago, where he demonstrated these methods in sort of analytic current flows or flow fields. And so far, they've only been developed for sort of static two-dimensional flows and for time optimal trajectories. And so we're going to build off of this in the first chapter that I'm going to share later. And so the methods we've discussed so far require global information about the environment. And so what that means is if we look at the schematic below, we know about the currents everywhere, including forward in time. We might know where there are obstacles like islands or keep out zones. And with all of this information, we want to be able to find a globally optimal path. And practically, this is useful if you have a good forecast, right? So you need to be able to trust your forecast explicitly. On the other hand, if you're operating in an environment that maybe doesn't have a forecast or doesn't have a forecast that you trust very far into the future, you want to make decisions based on local information. So allowing you to still be intelligent when you can only sense the currents from the vehicle. So in this schematic, we have an AUV equipped with an acoustic Doppler current profiler, which might allow you to measure the currents in situ. And so because you don't have all of the information, we want to develop methods that are near optimal, but of course, they're most likely not going to be as good as the globally optimal solution. Okay, and so with a little bit of background, today I'm going to be presenting 3 chapters of my thesis, all on this problem of energy optimal trajectories for point-to-point transit. So the first chapter is going to be focused on globally optimal solutions, so extending those ODE-based methods we talked about a little bit before. And then in chapter 2 and chapter 3, we're going to move towards onboard planning. So in chapter 2, we're going to do this with a sort of machine learning data-driven framework and focus on planning in horizontally varying currents, so a vehicle either at the surface or at a constant depth. And then in chapter 3, we're going to design a behavior that's sort of more motivated by the sensing capabilities we have on an AUV today, and just think about how we can plan vertically. So how we can take advantage of how ocean currents vary as a function of depth. So if we start with chapter 1, titled Energy Optimal Path Planning for Autonomous Underwater Vehicles with the Maximum Principle. And this paper is currently in review at IEEE JOE. And what we're going to rely on for this work is a classical tool from optimal control called Pontryagin's maximum principle. And the main thing I want you to take home is that this method is going to enable us to solve our problem to formulate our problem as a 2-point boundary value problem for ordinary differential equations. So PMP is going to tell us what differential equations to solve. And now numerically, we just want to find these boundary conditions. And we'll go through this figure later, but if you keep it sort of in your head, if you can see my cursor on the right, we have a boundary condition at the start. So the green dot, we're trying to find trajectories that get up to the yellow dot. We have ordinary differential equations that are going to govern all of these shaded gray lines in the background. And we want to find the trajectories that connect the 2 points, right? And then we'll be able to evaluate those for which one is our globally optimal solution. So if we go through the equations a bit more formally, and this might look familiar if any of you are sort of more familiar or are familiar with Hamiltonian mechanics or that type of formulation. So if we recall our problem statement where x is the state, v is the control, and u are the currents. And then our dynamics, again, are the control plus the ocean currents at a given point. We'll define 2 new variables. So p is the adjoint vector, which is in the same dimension as the state. And then our Hamiltonian h is how we enforce our minimization or maximization. That's how we enforce our optimization quality. So we have one term in the beginning that's looking at how our dynamics are aligned with the adjoint vector. And then we keep track of our cost function or our running cost, which is energy consumption, as you saw in the previous slide. PMP tells us that the optimal control is the value of v that maximizes the Hamiltonian at any given time. And we'll notice that our control in terms of direction is just going to point in the direction of our adjoint vector. And then the optimal speed is only a function of its magnitude and our dynamic power coefficient. And lastly, the boundary value problem that we can solve is defined by a coupled set of ordinary differential equations. So we have dynamics for our state, which again was given before, and then we have dynamics for our adjoint vector. And we have the same boundary conditions that we had before, but we have a third additional boundary condition on the Hamiltonian at time tf. And so if any of you are not as familiar with optimal control, but might be more familiar with ocean waves, these equations might look very familiar to you. So on the left, we have the Ray equations for deep water waves. We have dynamics for, again, their propagation in x and their wave number vector k. And then on the right side, we have the same equations for optimal AUV trajectories in terms of their dynamics x and then the adjoint P. And so what you'll notice is that these look extremely familiar, or they look almost exactly the same, right? So the vehicle or the waves are going to be steered by the direction of K, just as an AV is steered by the direction of P. The group speed, similar to the optimal speed, is just going to be a function of their magnitude, and then they're advected by the ocean currents. Additionally, the way wave number updates is exactly the same as the way an adjoint vector updates, and that's going to be given by the spatial gradient. This nabla x is the spatial gradient of the ocean current field. So your vehicle is going to change its direction as long as there is some gradient in ocean currents. And so the way we use this formulation to actually generate solutions and why it's useful is that it turns our optimization problem into a finite dimensional route finding problem. So in the simple schematic on the left, here we have a situation for no currents, which is why the background is white. We have, again, our starting point in green going to our ending point in yellow. And each of these gray lines is going to be one of these trajectories that's just going in a straight line because there's no currents, right? So the fastest way to get anywhere in a flat domain with nothing going on is just to walk in a straight line. Now, each of these trajectories is going to be deterministic based on its initial heading, right? So because we have deterministic ordinary differential equations, if we pick the initial value, we can shoot these forward in time. And so each of these rays corresponds to the x-axis here, so an initial heading. The y-axis is the time along each of these trajectories. And then the color is going to be the difference from any point along here to the goal, right? So we're looking for trajectories where this distance is close to zero, or in dark purple on the figure on the right. We can also look at solutions as where this dashed line and the solid black line are crossings, which is just the zero crossings for both x and y separately. So we see in this case, right, there's one solution. It's a rather simple environment. So if we take an initial heading of 90 degrees and we propagate it for unit time, that point through our dynamics is going to map back onto our trajectory in physical space. Now, if we make the environment a little bit more complicated, right, so we're going to add currents on the left, you'll notice that all of these trajectories are sort of swirling around, taking advantage of different currents. This complexity also maps onto the space of initial conditions. And now we have three sets of crossings given by the blue line, or the blue dot, orange dot, and green dot, which are all solutions to our boundary value problem. And so this is what we mean when that it's a sort of necessary condition. So the blue dot and green dot are lower on the y-axis, so they're getting there faster. And so those are actually globally optimal with respect to the orange dot. So if we look at where the blue trajectory maps from initial conditions to path, orange the same way, and green, we see that the blue and green paths, even though they end up covering more distance, actually take less time because they're able to take advantage of the currents. So hopefully that gives you a little bit of intuition on how these things are steered or maneuver in physical space. But we can also use this method to talk about or to think about the optimal speed. So again, where I want to minimize energy, so we're allowing our vehicle to speed up or down. And it kind of reveals this parameterization that we'll say is the magnitude v naught star, which is the optimal speed of a vehicle in no currents. And that's going to be just dependent on our hotel load and dynamic power coefficient. So what this means is that you might have different vehicles with different configurations, but as long as that ratio is the same, they'll want to go the same speed and no currents. And you can think about this intuitively by saying on the x-axis, which is that ratio beta over alpha, as hotel load increases, right, it costs more just to keep the vehicle running, so it wants to go faster. So its optimal speed and no currents on the y-axis is going to increase. Whereas if beta is zero, it takes no energy to put a vehicle out. It's just gonna use no propulsion and drift around and hope that it gets to the endpoint. So with this parameterization, we can also non-dimensionalize everything and think about how the vehicle is going to speed up or slow down based on the currents. So now in this plot, the x-axis is the along track current, and so that's the component of ocean currents that's pointing where you want to go. And on the y-axis is how fast the vehicle is going to go if it's operating optimally. And you'll see that if the vehicle is in a headwind, so it's working against the currents, it's going to want to go faster in order to traverse them more quickly. And if it's working with the currents or it has a tailwind, the vehicle will slow down. And so that was kind of a broad overview of the methods, but we were able to demonstrate this in very realistic, sort of high resolution, tidally forced environments. So on the left is model output from a regional MIT GCM, courtesy of Matt Maslov here at Scripps. And before you even look at the paths, if you just think about, or if you look at the currents, you'll see a few features. So you'll see this accelerated along coast flow, right? So that's something the vehicle is going to account for. There's a the clockwise rotating large scale eddy in the center. And then you'll notice these sort of rotating oscillations, which is the effect of the tides. And so each of these dots represents a vehicle based on a different parameterization. So the blue line is a slow vehicle, or a vehicle that wants to go slow and no currents, down to the red line, which is a vehicle that wants to go fast. And you'll see the fast vehicle, right, is going to take an almost direct path. It doesn't care much about what the currents are doing. While the slowest vehicle is going to take its time, it meanders around that eddy and is even reacting to all of these sort of time-dependent change in the environment in order to save energy. We also demonstrate this method working in a much smaller and more dynamic environmental regime. So this is an output from ROMS near St. John, U.S. Virgin Island. And this output was courtesy of Seth McCammon and Gordon Zhang at Hui. And you'll see here is we have very intense tidally driven flow flowing past this headland and creating a strong eddy that spins up and slowly advects out of screen. So for a slow vehicle that wants to go about 0.25 meters per second, in the beginning, it can't even make way towards its target. And so it's going to take a large detour up and around the eddy into the lee of the island until it can finally wrap back around. So in summary, and especially for the sake of this talk, chapter 1 really is a way to develop new methods focused on energy optimal path planning using ordinary differential equations for their computational advantage. And we're going to explicitly take advantage of this in chapter 2 by generating a large ensemble of optimal trajectories, which we can then use for some machine learning. And so after this chapter, the next two things, just as a reminder, are going to be focused on onboard planning. So what can we do if we can only if we don't know anything about the environment beforehand and we just want to depend on our sensors? So chapter 2, titled Energy Optimal Path Planning for Autonomous Underwater Vehicles via Imitation Learning and Transformers, which is currently in prep. And the two words I want to key on are imitation learning. And so that's going to be our form of machine learning, where we're using methods from chapter 1 to generate a large ensemble of optimal trajectories. And these are going to be sort of what we want our model to mimic. So that's going to be sort of expert behavior that we want the model to imitate. And then transformers are the type of model architecture we're going to use. And if you've heard the terminology before, they've gained a lot of popularity in recent years during doing natural language processing or for LLMs. And they're useful to process information in sequence. So that's how they're going to relate to optimal control. And just to call out, in this chapter, we're going to be focusing on planning in the horizontal, so currents that only vary as a function of x and y and are stationary in time. So we want to train some sort of machine learning model. And first, I just want to talk about what goes in and what comes out. So on the left side are our inputs. So we have for each trajectory, we have its time along the trajectory. We represent its state in terms of a distance and heading to the goal, as opposed to just x and y. The vehicle, we assume, can sense the currents at its single point in space, and we'll rotate those into a cross track and a long track reference frame. And then we have our last variable, which is energy to go. So this is the only thing that can't be directly sensed in situ, but we're going to use it as an estimate to sort of drive the model. So all you need to do is provide the model with how much energy you think it might take to complete the rest of the trajectory, and that's how it's going to learn what to do. We're going to predict two control actions. So it's, again, going to be the magnitude and direction of our vehicle, and we're going to predict them in sort of these polar coordinates. Okay, and so we want to use these transformer models, which process sequential information. And we're building this off of a recently developed decision transformer by Chen et al. In 2021. which was then applied to some aerospace work last year by Gafanti et al. The main idea here is that we take all of those features, so again, our reward, state, environment, action, we stack those up in sets of 4, and those are going to repeat along the trajectory. So that's how we're inputting our information into the model. Now our model, from this sequence, it's trained to predict one step at a time. And so from the state element, if that's the last element in the sequence, it's going to predict the environment. So this is our loss function at the top, which will sort of build up as we're training. So the model learns to predict something about the environment. Next, from the environment element, it's going to predict the action. So obviously we want our model to learn the optimal control. And then from an action, we want the model to predict the state. And so you want the model to learn something about how the dynamics of the system are working. Lastly, we want to add some regularization so that we might tune the behavior of our model. And so originally we were noticing that the machine learning model would sort of drift in realistic ocean currents. So we're going to add this regularization parameter lambda that weights how we want to learn optimal control against how we want to learn just going in a line. So if we know the currents and we know where we are and where we're trying to go, we can calculate just the control that it takes to go in a line. And when lambda is 0, we're just learning the optimal control. And then in the limit that lambda equals 1, we're telling the model we don't care about the optimal control, we just want to learn line following. So training, just a brief note on training is that we're using what's called teacher forcing with a single step rollout. So what that means is as we're minimizing this loss function over our data set of all of the trajectories and then subsequences up to the point of prediction, the model is fed in a ground truth sequence, right? So it's never learning to actually predict out a whole trajectory. It takes a ground truth and predicts one step out in time. And then it should be an emergent property that once the model is actually driving, it can sort of stitch together these predictions to make a sensical path. But it's not actually predicting or training based on full trajectories. So we have our model framework. We know what we want to put in. We know how to solve for optimal trajectories, but we want to generate our data set in some way that we can sort of simply and efficiently generate many instances of ocean currents. So because we're doing something with supervised learning, we need a lot of data. And to do that, we're going to use a framework where we're training in synthetic currents. So on the right-hand side is an example of one of these instances of synthetic currents. And that's going to be made up of a uniform flow component. And then we use a Helmholtz decomposition to specify spatial variability. And that just means there's one component that's divergent, and then we have one component of the flow that's rotational, and that's sort of these eddying features. And the statistics for each of these 3 things are going to be fit to our operational area in Southern California. So once we fit these statistics, we can generate many instances of the flow, therefore many versions of optimal trajectories. And then that's going to allow us to test our model back in the realistic ocean currents. But we never use the model to actually train. And so just to drive home why we're doing this is that we're going to end up training on 8,000 different independent samples of an ocean flow, where in Southern California, even though we have 2 years of hourly data, if we look at the temporal autocorrelation and do some subsampling, we can only get about 300 independent realizations. So before we look at the sort of whole data set, I'm going to show 2 examples of representative trajectories. So in each of these figures, the background is going to be currents from Southern California. We've just rotated and normalized so that everything is going unit distance along the y-axis. The red line is going to be line following. So that's our baseline and what we do sort of normally today. The green line is going to be the true optimal control. So that's sort of our training data that we want to approximate. The black line is our model without any regularization. And then the dashed line is a second model we've trained with the same sort of framework, but with a little bit of regularization. And in the upper left corner, in the legend, we're showing the relative energy savings with respect to line following. So given by this equation here. So that means a positive number is we're saving energy, we're beating line following. and a negative number, we're doing worse. And so the first example on the left, that's sort of highlighted here, and will turn out to be actually very common in our data set, is that in weak currents, the machine learning trajectories tend to drift, right? So you'll see that the green line and the red line are actually very close together. So in weak currents, we're not actually gaining any much by doing anything intelligent, right? It only saves 1% of energy. But our machine learning model is trying to do something clever. So it sort of drifts along with the mean flow that's going mostly to the left. But there's never any sort of flow reversal that's going to help it get back. So it ends up actually being over 10% worse than the model. By adding some regularization, the model is going to stay essentially in between the red and the green lines, right? And it's going to save you a little bit of energy, but at least it's not doing worse, and it's sort of doing what you would expect or what you'd want it to do. In the second example, we're crossing a very strong jet that's going right through the middle of the trajectory, where now you'll see all models outperform line following because line following is doing something very unintelligent, right? It's crossing this very strong flow, essentially heading straight into it for the entire duration, where all three, or the true optimal and both of the machine learning models, learn that you should cross this strong flow at a perpendicular. And then once you cross the jet, you can point straight to the target. So when there is energy savings to be had, it seems like the machine learning model is actually performing fairly well. So now we'll take a step back and look at sort of the full data set. And so just as a reminder, we're training in 8,000 synthetic currents. We're then testing in around 300 snapshots of currents from the MIT GCM. And we're going to be looking at these plots where the x-axis is optimal energy savings. The y-axis is how well the model does. And then the color is going to represent sort of like a heat map for all of these different data points. And you can read that as the probability of machine learning savings given a value of optimal savings, right? So if we're looking at the left, that's saying when the true optimal is actually only saving you about 1%, how well is my machine learning going to do? And this green line is 1-to-1, representing an upper bound. And then the blue line, 0, is when we're performing just as good as line following. So ideally, we want all of our data to sort of fit in that bound. So we're going to compare the effects of regularization. So on the left, we have a model without any regularization. On the right, we have regularization with lambda equals 0.5. And if we focus on the one on the left, right, you'll see that we're not doing very well. And so we actually see that a lot of the data set offers sort of minimal optimal savings, right? So the gap that we're trying to shoot for between this green and blue line is very small, and any deviations that the machine learning is going to make end up being punished and sort of actually being worse than line following. So this is representative of sort of a lot of situations that look like this, where we have weak currents, and therefore the optimal thing to do is actually more or less go in a straight line. However, once we add a little bit of regularization, right, and tell our model that it's okay to be more similar to line following, we get a variance reduction. So we decrease a lot of this spread underneath the cyan line. We push everything, or we clean a lot of it up, but we also get a bias down in performance. So when there is more energy to be saved, so further to the left, we get data points that were sort of along that optimal line, so almost near optimal, get biased down and away. But we do see overall that when there is more energy to be saved, the machine learning model is able to take advantage of that. And so in summary, we developed this machine learning framework to train off of a data set of optimal trajectories. And more so, we do this training in synthetic currents, and we demonstrate its success in an MIT GCM. So on average, we understand a little bit more about the upper bound, so what we're sort of striving for. So true optimal in this environment saves about 5% of energy and up to 20 or exceeding 20% in the most favorable currents. And this was for a nominal trajectory of about 100 kilometers in a vehicle with a nominal speed of about 0.75 meters per second. And lastly, with the machine learning model with some regularization, we find that on average, we're doing just as well as line following, right? So it's at least robust in that sense. Um, but when we do have favorable currents, so when there are optimal savings to be had, it's able to achieve them. So for the last chapter, titled A Greedy Depth-Seeking Behavior for Energy-Efficient Transits by an Autonomous Underwater Vehicle, and this paper was published last year in JOE. We're going to focus on planning in the vertical, or looking at how currents change as a function of depth and how we might exploit them to save energy. So the keywords here being greedy, which we'll say is sort of a locally optimal view, meaning that we're not looking into the future at currents, we're not looking at what happened before, we're just making a decision based on what we're sensing sort of right now. And again, we're focusing on vertical variability. So the currents here are a function of, we'll say x is a long track, z is depth, and they're also varying in time. So before we talk about the behavior, we can talk about a little bit of what's going on in the environment that our vehicle might be able to take advantage of or should consider when planning. So here is a time series of vertical current profiles in the Southern California Bight from our model. So the x-axis is about a month of data from 2016, or a month of model output from 2016. Y is depth, and then the color is the along track component of the ocean currents. And so you can see two sort of primary features. One is that currents are stronger at the surface, and they generally decay with depth. But the other thing that you should notice is that they're banding about twice a day, right? So you have very clear tidal signal in this model, and that's going to affect how the vehicle plans. And you can also see that it's not constant as a function of depth. So there is some nonlinear internal tide that's giving this tidal structure, or that's giving this tide more complexity also as a function of depth. It's not just sort of sloshing back and forth. These currents also change very quickly as a function of distance. So we're going to be looking at a 120 kilometer transect. So that's now on the x-axis. Y-axis is depth, and color is the same as before. And this is one snapshot in time. And our vehicle wants to be able to plan through something like this. So you can notice that, especially in the surface layer, we'll actually have a flow reversal, meaning that in the beginning, flow is going against you. At the end, it's going strong for you over the course of a single transit. So if you were just operating in the surface zone, right, you might get punished in the beginning, and then you might pick it up a little bit at the end. But if you could think about something and do something adaptively, you might be smart about avoiding it in the beginning and then making your way up to the surface as you finish the trajectory. So our behavior is going to be based on minimizing energy consumption per unit depth, or DEDX. And this is sort of building off other work in our group by Justin Chang in 2022 and Mark Anderson more recently, where they've developed this power model, calibrated it to some of our vehicles, and then looked at changing the control of our vehicle during constant depth operations based on the same value. So DEDX, you can think about sort of like miles per gallon in your car, just inverted. So we want to get the least amount of DEDX, and that's going to be our power over speed over ground. So just a quick note, because we're making the vehicle sort of travel in a straight line horizontally and just changing in depth, the two control parameters are propeller speed, which maps directly onto its speed through water, and then the depth, which will give you a different value of current based on where you are. So again, our power is a function of propeller speed, and our speed over ground is a function of prop speed and depth. So the behavior works in sort of three pieces. So first, you're going to sense the currents, and we're designing this behavior for an AUV that has an upward and downward facing acoustic Doppler current profiler. So it's going to be able to sense ocean currents above and below the vehicle with some limited range. Once it takes a measurement of ocean currents, it's going to calculate what is the potential DEDX if I were operating at any of those depths that I was just able to sense, and then operating at any RPM that's within my range, right? And so once we do that calculation, we can just pick out whichever is best right now, And so if we're starting at 400 meters, this would tell us I want to move up in the water column to about 150 meters, where we have this strong along track current, and I'm going to operate at around 350 RPM. Once it does this sort of thinking, that will be commanded to the vehicle will change depth and adjust its prop speed accordingly. So all of this work, or all of this behavior is sort of looped through and done repeatedly as we complete a transit from start to end. So these are two examples, and we were analyzing this behavior with respect to a realistic sensing aperture. So a 1200 kilohertz ADCP is able to sense about plus or minus 10 meters above and below the vehicle. And that path is shown on the top in red. And then on the bottom, this is going to be our upper bound or lower bound on energy. So the best we can do is if we can sense the whole water column. So no matter where you are, you're always going to be able to move into sort of the most advantageous region. So the background is colored by our DEDX. So the vehicle the whole time is searching for these areas of light color. You can see the effect of limited sensing where around 80 kilometers with full water column sensing, we're able to jump instantly sort of up to the surface. This is actually, the aspect ratio is off, so it's not doing something instantaneous, but with respect to the length of the path, it's able to sort of quickly get to the surface and ride these strong currents, whereas the vehicle with local sensing is more limited and stays at the bottom until it completes the trajectory. So in this paper, we looked at some statistics of these behaviors over the same 2 years of MIT GCM output, which resulted in about 17,000 trajectories, which we can compute statistics over. Again, the currents are time varying. And we also looked at the effect of where the vehicle started in the water column. So because we only can sense a limited range, it does depend on where you start. And we were looking at these three trajectories in the Southern California bight. So we had one offshore, one cross-shore, and one alongshore. In general, the results I'll talk about today are consistent across the transect, so we're not going to go into all of that detail, but we're just going to show a few results. So the first thing we want to show is this PDF on the right, which is the probability density function of average energy consumption. So from our 17,000 trajectories, right, we look at the statistics of energy consumption and plot them as a distribution. The dashed lines are going to be a vehicle launched in deep water. So the dark blue is a deep vehicle, the light is a shallow vehicle, and the dashed line is because they're operating at constant depth. And what you'll notice is that when you're operating at the surface, you have much more variability in your energy consumption because you have stronger currents. And then if you sort of play it safe and just operate deep, you have less spread. So you're in general going to do about an average of 40 watt hours per kilometer. And it's not going to vary very much because the currents themselves don't change a ton. Now, once we add our adaptive behavior, which is where we go from the dashed line onto the solid line, you'll see sort of very straightforward increase in performance. So on the right side of the distribution, a lot of these worst case scenarios, right, move left. So it's less often that we're spending more energy. And then on the left side of the distribution, from the dashed line up to the solid, we're moving up into the left, meaning that it's more likely that we're using less energy. Right? And so for this setup on average across the entire data set, we again save about an average of 5% of energy using this adaptive behavior with a limited sensing aperture. And then we have maximum savings exceeding 20%. The last thing we wanted to do in this work was see how the vehicle is actually responding to a physical process. And that ended up being tides. So the way we did this was by looking at sort of a large data set of trajectories. So again, we have 17,000 of these trajectories of depth as a function of distance. And then we'll make a modal decomposition of that depth variability, resulting in these colored modes. So we remove the mean, the dashed line, we take an SVD, and each of these colored modes is representing how the vehicle might dive or climb with different frequency. But importantly, now if we actually analyze the amplitude of each of those modes, and specifically their frequency content, we get the power spectrum on the bottom of the page. So on the x-axis is frequency in cycles per day. On the y-axis is the power. So essentially how large are these swings up and down. And each of the colors corresponds to, again, the same mode on top. But the important part is that we notice that each of these modes has the same matching or the same frequency as the dominant tidal constituents in the region. So if we're looking at launches hourly across 2 years, we actually see the vehicle makes decisions at the same frequency sort of as the tides in the background. So that we believe was sort of the dominant feature that these vehicles or that this behavior enabled you to key off of to sort of adapt and save energy. And so lastly, I know I've talked a lot about simulation today, but this work has actually been actively developed and tested locally through a great collaboration with a few undergraduates here at UCSD and both through the MPL intern program. And what I'm showing on the right is some data from an experiment right off of the pier here. So the yellow line is the depth of a vehicle as a function of time, and it's going to complete 3 transects. So that's where these 3 sort of the 3 straighter lines are. The first 2 are going in one direction, and the last one is flipping around and going the other direction. The one thing we updated for this onboard test is that instead of just using the sensing aperture of an ADCP, it's actually going to complete a dive to sort of build up more environmental knowledge. So after it builds up a profile of the currents, we can then do our DEDX calculation and pick the optimal depth to operate at. And so the first 2 transits, it's going to choose sort of a shallow depth. And then when it flips around, right, the same shallow depth would now be a headwind. So it's going to operate at depth. Mirrored below, we can see on the y-axis is DEDX. Below this dashed line is its energy consumption in no currents. And so because we're achieving sort of green values along these transits, shows that our behavior is actually selecting currents that are beneficial and reducing energy consumption. So in this test, I think we achieved more than 20%, especially on these strong sort of tailwind currents of energy consumption. And this is a figure published from Trevor's paper last year. Okay, so in summary of chapter 3, we focused on vertical variability of ocean currents, and we designed our behavior to exploit the vertical shear. With a realistic sensing aperture, we were able to achieve around 5% of average savings and always outperforming constant depth operations. And then through a modal decomposition, we showed that optimal paths oscillate actually at tidal frequencies. And again, as we just showed, some of this has been tested locally. So to sort of summarize and take a step back, I just want to say that while we've worked on different pieces of this, they all sort of fit in a larger system of an autonomous vehicle that all of this work that we're doing in our group and other people around the country are all sort of contributing to in parts. And so I've gotten the chance to sort of work on a bunch of different parts of this puzzle besides what I've just presented today. So I've gotten to work a lot with sort of vehicle modeling with Mark's work, doing power modeling for both the Remus, and then some work with Ryan and Andre on the wave glider. Again, chapter 1, sorry, was about this global optimization for optimal trajectories. And all of this can be done sort of in practice in terms of pre-planning. So this is as long as you know what the vehicle does, you have a good forecast, you might be able to find something that a vehicle should do once it goes in the water. But of course, it's not in the water yet, right? So then we have to deploy. So we might go out on a ship or do this from shore, throw in all types of vehicles into the water. And then even though we might have a plan, something to do, we want to enable the vehicle to still update its decision making and make smart decisions based on this sort of paradigm of sensing, thinking, and moving as it makes its way through the water column. And eventually, you'll end up getting to a recovery, hopefully. So that's going to conclude sort of my main part of my talk. As tradition at Scripps, I get to at least, before I do Scripps friendship collage, of course, we have some great acknowledgements of the people who really made this possible over the last sort of 5 or 6 years. So first and foremost, my advisor, Sophia, who has just been giving me great advice and always encouraging me to sort of pursue my interests and supporting me in my research. Thank you so much to my committee. Um, Eric has always given me good advice, always been around, and also a big part of ChordC, so I couldn't have been here without him. Mark for his expertise in research, but also helping me teach. And then Dan, Bruce, and Sonia all really giving me good advice and feedback along the way. I want to acknowledge my funding. So most of my research was funded on the NDSEG Fellowship through the Office of Naval Research. Um, Huge shout out to people who run the graduate department, Gilbert and Dana. Um, a huge a huge part of this work wouldn't have been possible without Hunter. So Hunter was a great mentor and collaborator through a lot of this work. And it really started actually as the Scripps peer mentor program, just getting coffee and chatting about grad school and life. And we ended up sort of publishing papers together, and it couldn't have been a better sort of friendship and collaboration. Matt, Seth, and Gordon, who gave me model output to sort of hopefully ground my simulations in the real world. And then all of ChordC, so many of you are here in the room today. There's too many of you to list, but it's just been such a joy to come to work every day with people who are so smart and driven and nice to work with every day. So special shout out to Sean Kitchen and Kaylee, who have been my office mates through the past years and kept me sort of sane every day. What's last? Two great undergraduates who I had a chance to work with, Trevor and Aaron. Um, just a pleasure to work with. Everyone who made fieldwork possible. So the crew of the 3 research vessels I've been on, everyone at Palau CRF, and then people who I've been on sort of cruises, took me under their wing on cruises, Luke and Angel, and then Pat Welch, who I think was on almost every cruise I've ever been on. And lastly, just all of the other AOS students, everyone from the 2020 cohort. It's been wonderful. So yeah, this has been a time that's like, I don't know, just a very special and long part of my life. Um, Not only seeing some like beautiful places that I would probably never get to see again, or would have never gotten the chance to go to, all of my friends and coworkers who have spent so many hours on these boats together, and then getting out into real life every once in a while and having fun and seeing the world. But really, the biggest thanks is to my wonderful wife, Allie, who has just supported me so much over the past few years. My 2 beautiful cats, Bao and Bunny, who have kept me sane and sit with me while I work. And then my parents, Margie and Wes, and brother, who have just always supported me no matter what, even if they ask me if I'm going to get a job, which maybe I will, maybe I won't, but I don't know, just endless support over the last few years and obviously before that. So with that, I will leave up sort of some take homes, and I'm happy to take any questions. We're going to try to do the lights, but maybe that's not going to work. But if there's any, we can start with questions in the room, and then on Zoom, Kaylee and Sophia will be like monitoring. And if you have any questions in the chat or raise your hand, we should be able to also hear you in the room. So, yeah.
Why do you develop a machine learning approach instead of just building on your method in chapter 1? The methods in chapter 1 not like apply to a certain situation that you're to implement.
Yeah, so what we developed in chapter 1 required you to know everything about the currents. So to find these, to optimize the path, right, they have to be able to sort of try all of the trajectories through the world, and that includes both forward and time. So in chapter 2, if you're only able to sense currents where you are, and you actually want to build up knowledge as you're driving, we wanted a way to sort of instill that into a machine learning model. So while the data comes from a globally optimal solution from chapter 1, or the actual trajectory, all of the data that's training the machine learning model is just sort of point measurements along the path. So it doesn't actually know anything about what's going on around.
Thank you, Ben.
Yeah.
Question from the audience. Sorry.
Yeah.
Hi, great presentation. I just had a question about chapter 2 and 3. If I understand correctly, chapter 2 looks at what happens on a horizontal plane, and chapter 3 looks at what happens in the vertical.
Yeah.
Based on your understanding of the problem, what would be a good way to put these two together, looking at the 3D?
Yeah. So I think there's two sort of main parts. So one is for chapter 3, we can sort of we know something about the vertical just because that's the natural way, like an ADCP is going to be able to sense in the vertical. And the scale at which things change in the vertical is much smaller. And so you'll able to sort of pick up on those gradients effectively. Scales on the horizontal are sort of much larger. And so the only way that we were able to sort of build up any information about them is actually driving sort of larger path lengths in that sense. Obviously, you want to be able to do both things at the same time, ideally. And so some of the methods in chapter 1, we do some toy cases in 3D, but there's sort of additional problems or sort of numerical issues that come up when you're doing this in 3D. But I do think or yes, to take one step back of that, I think part of this was thinking about which environments you like maybe want to plan in. And so if you know something about the scales in the environment, maybe you actually don't need to consider 3D and you can just do 2D in either depth or sort of horizontal. And so from what we were able to show of the vertical behavior, which I think is actually much simpler and like a little bit easier to implement, and especially for Southern California, where we do actually have these like strong vertical shear, it's probably a more straightforward and you get just about the same benefit by sort of just exploiting the vertical. But there is this interesting problem that we haven't fully been able to sort of answer yet, but is understanding that parameter space of like smoothly when you should plan in 2D or 3D. Like those are probably limits of the problem, but there are obviously environments where you would probably want to do something intelligent in all three. Yeah. Mhm. Yeah.
Also, with respect to chapter 2, you mentioned a transformer-based, machine learning-based
Mhm.
approach. You mentioned you had like kind of synthetic data,
Mhm.
I think about 8,000, a few thousand samples.
Mhm.
How long did it take to train your model? Was it like very quick, a few minutes, or?
Yeah, it's not a super large, it's not like a super deep or large model. So the whole model trained is about like 50 megabytes. So we're not talking about like this massive gigabyte model. Training on a cluster of a few GPUs is about like 20 minutes. So we're able to iterate through different models relatively quickly. But yeah, you could, I'm sure, blow it up to like some massive machine learning model, but we're trying to keep things like relatively compact. Also with the view that if they're sufficiently small, you could more easily like actually run them on onboard computing and not require like a GPU to be sitting on an AV. Yeah. Mhm. Yeah, Dylan.
So do you think you might want to apply this like transformer-based model to like chapter 3? So rather than maybe having a 3D algorithm, you could obviously like simulate in the horizontal, like vertical
Mhm.
currents, and then apply the transformer approach. Or do you think that like wouldn't make sense for that context?
No, I mean, I think you definitely could. There's two. So in real life time, those things happened in opposite order, which is why we sort of started more simply and then went to machine learning at the end. Um, but I don't think there's a reason to not try sort of different approaches or maybe like a machine learning thing for depth, especially as it might give you sort of some context as you're driving. And so that's sort of the main idea, right? Is maybe something previous in the path could inform what you do further along, and doing some transformer or machine learning could help with that. One of the issues was especially how we generated data for chapter 2 is that our optimal trajectory from chapter 1 works very well in the two-dimensional environment. And it's not explicitly because it's 2D, but it's because the aspect ratios is sort of nice. And sort of before I get sort of too down in the weeds, it's just if on the vertical chapter 3, we had 120-kilometer transit long by only like 600-meter depth. And so the method that we developed for globally optimal planning through that in realistic currents just gets a little bit sort of numerically unstable. So you might need a different method. If you want to do the exact same thing, we would need to think a little bit more about like how we build up our training data. But there's nothing wrong with, I think, taking that approach to sort of help the greedy behavior do a little bit better.
Thank you, Ray.
Yeah.
Okay, we're gonna take a couple of questions on Zoom now. So Mike, do you want to ask your question? Can you unmute?
Hi, yes. No, this is all really great. So have you thought about what the optimal policy might look like for the depth profiling behavior? Like in particular, where the executed behavior, where you were exploring the currents by physically moving the vehicle up and down. So how often should you perform a depth transect versus exploiting the information?
You mean in terms of when we were like building up the profile of currents? So like
Yeah,
how
that's right.
yeah. Um, that's a good question. I think for what we looked at in Southern California, where we had sort of nominally like a 1 to 2 day transit, um, you would probably want to, I don't know, reset on the order of, so like on the order of the tide, so maybe one every 6 hours or so. That seemed to be like the dominant sort of time scale that at which you're changing. You might get like an actually like very large change in the ocean current. So then you might fully want to resample the water column. But I don't think you need to do, if we look at, um, like if we look at something like this, you're not getting a massive change every hour or on the minute scale. So if you start getting a profile, it gives you some sort of knowledge about the environment, and then let the sort of greedy behavior go. I think, yeah, resampling the whole water column on the order of a few times a day would be sufficient sort of in this environment.
Thank you.
Okay, now I'm gonna ask Matthew, can you ask your question?
Yeah, hi Ray. That was a really nice talk. Thank you very much. I just had a question about for this size vehicle, can you always assume that the extra processing power is negligible, as you evaluate some of these behaviors? That's just maybe a simple question. Hopefully the answer is yes, it's always negligible. But that got me thinking about whether, uh, you know, this issue of whether to use only onboard sensor information versus a model nowcast/forecast that you could in principle get transmitted to the vehicle if you were willing to surface. And so I guess I'm just wondering, did you explore any of that swap space of additional processing time versus gaining more information in order to optimize?
Yeah, really good question. So for most, or for, I'll start with this one. So the greedy behavior, the compute is negligible. It's, really just a few computations. I don't think it would reasonably affect the energy consumption of like actually up the hotel load, say by running these calculations. I haven't checked, but you could argue, or maybe you would want to investigate with some of the machine learning methods, especially as you make models that are sort of like deeper and larger. Obviously, or we would hope that you wouldn't spend more energy on the compute than the energy you would actually save. Um, but to your last point about adding a forecast, I think in the sort of like full systematic view, you probably should do that, and that should be part of your planning. So if you're going to be surfacing, right, you get a new forecast, you can even run some sort of like pre-planning or open loop optimization shoreside and just update the path. I think that's smart and probably is what should be done. And we want to develop these sort of smaller pieces that once you maybe update that path based on the forecast, you can still continuously update it and make it better as you're based on in situ sensing. But yeah, there should be this loop of maybe ingesting some new global information from a forecast or from shoreside, as well as integrating sort of in situ measurements.
Thanks a lot.
Okay, and then Tom, can you unmute?
Yeah, thanks, Sophia. Hey, great talk, and it's really great to see all this applied path planning stuff. In chapter 2, when you characterize the ocean space for your calculations by giving it percentages that certain things would happen, eddy currents or current strengths and things. Did you find ever that there was an area over which those percentages, broke down, or no? As in, you got too big of a space, you simplified it too much, and then your profiling broke, and then your path planning broke down.
Like, are you saying does the data set, did we find sort of like specific outliers in the data set or that weren't represented in our training?
Yeah. Over what area did that happen? I know the travel here isn't very far, so the answer is probably no, but I was curious.
Yeah, I mean, in general, we found that I would say that the parameter space represented a much larger sort of potential space of the ocean than the model. I guess if I'm trying to say that right. So yeah, I think the parameter space or the currents that we were able to generate were more expressive than what we saw in MIT GCM. There were a few outliers, sort of where we saw the worst case performance was when we had sort of very coherent eddies that were offset from the path. And I don't think that was necessarily because of a lack of information from the training data, but just sort of the fact of limited information. Like as you're starting, if you only have current measurements from where you are or just from a few measurements, you're probably never going to sort of build up a representation of this eddy that's sort of like offset, allowing that the global path might actually be able to like circumnavigate. So there are definitely cases where the ML breaks down, where you should be able to save a lot of energy, but I think it was more so for just the inherent like limited sensing capabilities rather than a lack of representation in the data set.
Great, thanks.
We'll take one more question from Ryan.
Yeah.
Kind of building off of that question, how much more would you need to do, or how much more simulations would you need to train the model on in order to make it more of a global model instead of sort of like a Southern California?
Yeah, so that's a very good question. I don't have an answer for you, like how much more. I think it would be, I don't know, it's kind of an open question of should we try to get our training data to represent Southern California so that it works in Southern California, or right, should we completely vary all of the parameters that we're using, give it every sort of example of ocean currents that you could find and build sort of like a foundation model, and then you can maybe like specify on top of that. But so far, we've mostly just focused on wanting to do this task of driving in Southern California. I think if you wanted to do something more global, it would be interesting to do maybe like a transfer learning thing. And I know we've talked about this, is like if you have all sorts of data that represents different types of ocean currents, you might be able to learn like very fundamental rules of thumb that you want the vehicle to follow. And then if you have fewer examples of data, like in Southern California, right, we don't have enough data to actually train it, you might be able to update your like global model on more local information to make it perform better. But yeah.
Okay, thank you all for the questions. This concludes the public session. Thank you for an excellent talk. Alcoholic beverages and food. I think Haley will lead you down to some side, and we will leave with next time.
Wait, are you host? Just make sure you pass it to me or Sophia before, so Sonia, I think, can stay on.